factors that are going to affect your aircraft's performance? Well, the first big one that we're going to spend a lot of time on is density altitude. Now, how does the FAA define density altitude? This, by the way, is a very popular private pilot FAA written test question. How does the FAA define density altitude, or what is the definition of density altitude? Well, the answer is this: pressure altitude corrected for non-standard temperature. And you, as a private pilot, are looking at that going, pressure out, what does that mean for me? Well, just know that for your written test. Pressure altitude corrected for non-standard temperature. Now, what is Jason's definition of it to help make it easier for you? It's where the airplane feels like it's at. Let me explain. If density altitude is 3,000 feet at the surface, your airplane is going to perform as though it's already at 3,000 feet. We know we get a decrease in performance as we climb up in a normally aspirated aircraft engine, which means it just breathes air. It doesn't breathe with the assistance of a turbocharger. That's a different story. But a normally aspirated aircraft engine, density altitude affects it greatly. So again, if the density altitude that day is 3,000 feet, my aircraft just rolling down the runway will perform and feel like it's already at 3,000 feet, meaning we will get a decrease in aircraft performance. The higher the density altitude, the worse the performance. Now, what are the three big factors that add to density altitude? Well, here's what increases density altitude: high elevation. If you start out high already, you're out in the Rocky Mountains, the Appalachian Mountains, you already are at a disadvantage because you're at a high elevation. The two big ones, though, are high temperature and high humidity. We get a lot of that in the summertime in Florida. High temperature, high humidity cause an increase in density altitude, thus giving you a decrease in aircraft performance. When those three things are high, high elevation, high temperature, high humidity, you get a decrease in aircraft performance. Now let's switch gears and talk about weight and its relation to our aircraft performance. The effects of weight. You get an increase in takeoff roll. A heavier aircraft takes more effort to get into the air and to stop when returning to the runway. You're going to get an increase in your takeoff and your landing roll. You're going to get a decrease in your climb performance of that aircraft. It's going to take a little more lift, a little more effort to get that airplane aloft. You're going to notice a reduced range. Previously, that same amount of gas could have got you 500 nautical miles. With an increase in weight, maybe it's only going to get you 400 nautical miles. And you also get an increase or decrease in aircraft stability. Now that's something interesting. Let's talk about that in just a second. I want to talk about maneuvering speed here first. Maneuvering speed, or VA, that is the speed at which the airplane will stall before exceeding its design limit load factor in turbulent conditions. You ever hear that, oh, it's getting turbulent, let's slow down my airplane. I want to get back down to VA, or certainly under VA. VA, maneuvering speed, is that speed at which, I'll put it in plain English, that FAA definition, here it is in plain English. VA is the maximum speed that if I'm in bumpy conditions, my airplane will stall before it breaks apart. It sounds gruesome, but that's what they're trying to explain to you there when they say exceeding its design limit load factor. It's a polite way of saying break apart, essentially. That's what they're trying to tell you in plain English. That's why knowing our VA, our maneuvering speed, is so important. And here's what we do know about VA, and I'll share with you how to calculate VA in a future lesson. VA, maneuvering speed, increases as weight increases. Why? Well, our VA, our maneuvering speed, goes up as our weight goes up. Why? Because it's harder for the same turbulent conditions to displace something that's heavier. The same amount of force is applied to a 2,000-pound airplane and a 1,000-pound airplane. Same amount of force. It's going to displace that 1,000-pound airplane a whole lot more than it will the 2,000-pound airplane. You get an increase in weight. You also get an increase in VA, or maneuvering speed. Now, this is why VA is normally calculated at maximum gross weight. Full fuel, full oil, max amount of passengers and baggage is how they calculate this. So then, assuming you don't take off at max gross weight and you continue to burn fuel, that VA adjusts and it kind of keeps you within that safe range. But know that calculation is based on you being at maximum gross weight. So you might have to think and make some adjustments that you might be lighter, thus get a decrease in VA for that aircraft's weight. So take VA as you read it in your aircraft's POH, Pilot's Operating Handbook, with a grain of salt, because it could be adjusted for that actual weight. Now let's talk about how that weight now affects our center of gravity and our CG. The center of gravity is the point at which our aircraft would balance. I just threw that red star down there. If this were a fulcrum or a seesaw, teeter-totter, whatever you want to call it, that is the point at which our aircraft would balance. That is our center of gravity. Whenever we mention the word stability, we're talking in reference to the rudder. Because if I were to enter into a spin, I would use my rudder to recover. Now, my rudder needs leverage. It needs an arm. So, for example, I would draw a line from my CG all the way back to my rudder, which creates an arm. And it's all about leverage. Have you ever tried to open a door and maybe the door handle was in a little bit or close to the hinges? Just visualize that with me. There's a reason the door handle is far away from the hinges on the door. It makes the door much easier to open. Now take that door handle and let's move it closer to the hinges. Let's move it to the middle of the door. How much more difficult is it to move and open that door now? The same is true with a wrench. When you grab a wrench, you grab it by the end to get as much leverage as possible. You don't grab it up near the front, near the bolt, when you're trying to make that adjustment. You need leverage. A forward CG, like you see here, gives us a longer arm back to our rudder, thus giving us more leverage, which ultimately equals more rudder authority, which gives us an increase in stability. Let's look if I had an aft CG back by the baggage compartment. Look how short my arm would be. It's like taking the door handle and putting it in the middle of the door, where the hinges are my rudder and the door handle is my center of gravity. I've got a shorter arm, thus I have less leverage, less rudder authority, and making my aircraft less stable. An aft CG makes my aircraft less stable. A forward CG makes my aircraft more stable. When loading an airplane, I want to focus on trying to have a more forward CG. I'm going to get a slower cruise speed, like 2 or 3 knots, but ultimately I'm going to have a more stable aircraft. When it gets bumpy, or if I was to enter a stall or a spin situation, I've got greater rudder authority and elevator authority to boot, and be able to make those proper recoveries and take those precautions. Always want to have a forward CG to equal more stability.